we are here to talk about near real-time Lakehouse ingestions with StreamNative's classic engine and Ursa. A quick intro about ourselves. We are technical lead engineers from Motorq, and I am Karthikeyan. I am part of the analytics team here at Motorq, and I build robust and scalable pipelines to support high-throughput analytics. And I have Sai here, who leads the next-gen initiatives at Motorq, which enables the generation of powerful insights used by our customers. So I have Saravanan here with me. He has experiences in building fault-tolerant distributed systems with tight SLAs. Okay, so before we jump onto the topic, I'll just give you a context on what Motorq does and the scale of data that we are dealing with. So Motorq sits at the center of the connected vehicle ecosystem. We transform raw connected vehicle data into actionable insights for businesses that own and manage vehicles. We are the trusted leaders in this connected vehicle space. We have integrations with top OEM partners and aftermarket partners in this automotive industry in US and EU. With all these integrations that we have, we get direct and secure access to raw telemetry and diagnostics data straight from the vehicles themselves. So all these OEMs and aftermarket partners ingest millions of data into our system. So once we have the data, we standardize and normalize for further analytical processing. We have built a highly secure and scalable system that is used for advanced analytics. So once we have this insights generated, we expose our products via different interfaces to our customers, starting from REST APIs, Kafka streams, Snowflake, and whatnot. We also have our own Motorq LLM agents that is built by us that solves the fleet managers' problems on a day-to-day basis. We also have a web app, which is the powerhouse of multiple features that we offer. And we have a wide range of customer base, starting with fleet management companies, telematics service providers, fleets, dealers, OEMs, and whatnot. And all our customers collectively operate some of the largest vehicle networks in the US. And all our customers require these vehicle insights in a real-time and scalable manner. So they use these insights to solve some of their use cases like optimizing their vehicle routing, analyzing their driver behaviors for safe and more efficient driving, reducing their fuel cost, preventing accidents through safer analytics, and also they use these to address their ongoing vehicle maintenance issues. And Motorq takes pride in sharing these insights to them with high quality for maximizing their ROIs and enhancing their business growth. And I'm happy to talk about most of the features that we offer in detail after the session as well, if you are willing to join. So for most of the use cases that I've mentioned, we want our data to be available in Snowflake. Now, let's just look at how we ingest data to Snowflake in our initial architecture. So it all started with our internal processing jobs ingesting millions of data into Azure Event Hubs. We have enabled capture in Azure Event Hubs, which made sure that the data is sent to storage account every 5 minutes. And we have created Snowflake stages in Snowflake that were pointing to these blob storage. And we were running custom ETL cron jobs, which was reading data from blob and pushing it to Snowflake native tables. So while this architecture worked well for our use cases at that point in time, but as the business needs grow and the real-time requirements scaled up, we started to see some opportunities to improve. And the first thing is latency. Since the pipeline was batch-driven, there was always a delay between the time at which the data is ingested in Event Hub and the time at which it was made available in Snowflake. Second thing is cost. So moving data from Azure blobs to Snowflake incurred heavy costs during peak loads. Cost was manageable early on though, but with higher volumes, it became a consideration. Third is batch processing. So to manage costs, we had to run our ETL pipelines with very less frequencies, which further slowed down the data availability to our customers. And here comes the maintenance part. The custom ETL jobs required ongoing maintenance and additional overhead. We have hundreds and thousands of custom ETL jobs running to sync from Event Hubs to Snowflake. So just imagine the maintenance overhead that we would face if we were scaling to 10x. Last comes the duplication. So as you have seen in the previous slide, we had data stored both in Azure Storage Account, as well as in Snowflake. So in short, this architecture gave us reliability and trust, but as our needs evolved towards scale, speed, and efficiency, we saw some room to improvise. And with that in mind, we started envisioning our next gen architecture with certain goals in our mind. First thing is real time insights. So we wanted to move from these hourly data syncs to sub-minute data availability, which means the insights are available to our customer much faster, which improves their decision making and enhancing their customer experiences. Second thing is elastic scalability. We wanted a system that seamlessly handles Motorq's growth and that too with cost not increasing linearly. So essentially, we wanted to scale more, but without linearly increasing cost. Third is operational efficiency. So by modernizing these pipelines, we not just wanted to reduce the ETL frequencies or latencies, but also to optimize on the infrastructure spends, thereby reducing the cost. Self-managed reliability. So our big goal was to reduce the heavy lift of maintaining additional custom ETL jobs. So we wanted a system with lesser manual intervention, fewer moving parts, and lower SRE overhead. In short, our next-gen system is all about scale, speed, efficiency, and simplicity. And that's when we got to know about StreamNative and Ursa. I'll have my team to talk about how Motorq leveraged the use of StreamNative and Ursa to achieve these goals.
Yeah, thank you, Karthikeyan. So, as we all here for the StreamNative conference, right? Everybody knows what Ursa is. Let me try to give you a quick overview of what it is and why do we love it and what are the benefits that we are reaping out of it. So, as you guys know, Ursa is a streaming engine that speaks the language of Kafka and Pulsar. If you are already running Kafka or Pulsar APIs in your system, Ursa is just a drop-in. You just plug out and plug in Ursa with it. And as you all know, Ursa is it has API compatibility with Kafka. It is headerless architecture, makes it cost efficient, and it is like Lakehouse native storage, which is a big selling point for us. And it also has better integrations with a lot of catalog integrations. Like first one is like Unity or Snowflake. We have a lot of catalog integrations, which makes data instantly discoverable, queryable, and it's easily governed for us. So this gives you a high-level overview of what Ursa is and why is Motorq using Ursa. Let's look at that in the next slide. So at Motorq, we have asked this question: if Lakehouse is a single source of truth, why are we running Kafka clusters or connectors or extra ETL jobs and maintenance pipeline just to land Kafka into the Lakehouse? Ursa just collapses all of these into one single system. Ursa, that's what I meant by Ursa natively supports Lakehouse. So this was a main selling point. Then we needed to way to cut down on the infrastructure costs without sacrificing on the reliability. So Ursa solved it by writing data directly into the cloud object storage. So it has both stream and table properties. So this eliminated the duplication cost completely for us. Then to simplify our data pipeline, so Karthikeyan mentioned our data pipeline was loaded with a lot of custom ETL jobs. We wanted to simplify this. And how did we simplify this? We started using Ursa for this. It completely eliminated the connectors, the extra custom ETL jobs, and maybe the Snowflake sync as well, right? All these things was moved out and we replaced it with Ursa. So our requirement was very simple. We wanted to stream the data directly into the Lakehouse without taking any extra overhead. So we wanted the data to be instantly queryable, and Ursa delivered it natively. So another challenge was duplication. The same data was existing in two places. First, the data we used for real-time analytics was in Snowflake, and the second time, the data that we used for our downstream app services were being streamed from the Kafkas. So we did not want to have this duplication of data. We wanted to have one single copy of data to power both these applications. So Ursa gave us this stream to table duality. The same data set is consumable as a Kafka topic for streaming as well as a table in Iceberg. Then comes in the schema registry and versioning part. So we were able to catch the invalid or mismatched schemas at the time of ingestion. The schema evolution is also applied safely across all fleets and OEMs without breaking the downstream services. Why does it matter? At Motorq, the schema evolves rapidly. We always wanted to do decoupled deployments without increasing the overhead that we do during deployments. So for Motorq, what this means is a more resilient system which is lower in cost, and we integrate faster insights for our customers. And for anyone running streaming plus Lakehouse today, Ursa offers a simpler and leaner path forward, which made it as a no-brainer for us to choose Ursa.
Yeah, so we'll just run into our next-gen architecture, right, how it looked like. So let's see, right, how this what are the needs we had? We had scale, speed, the cost efficiency, and reliability, pretty much which every company has, right? So what happens in the left is now our connected vehicles continuously stream the data, and these data, mind you, is like high volume, high velocity data, right? This directly flows into the Pulsar, into the StreamNative ecosystem, and Pulsar by default we know is built for the massive throughput, and it ensures proper durability, right? So from here the magic happens. From here we leverage the stream delivered to table, that is the external table functionality, and this particular functionality takes these streams and lands them directly into the tables, which is stored in our Azure account, thereby skipping all the previous ETL jobs and connectors that we had. So once this data lands in Azure storage, right, it resides there as Iceberg tables, which I mentioned, and each table here, that is each topic, corresponds to one single table. So this ensures that we have clear separation of the topics, and thereby we can do proper governance. Because previously our data had duplicates and deduplication, and with a scale like our company with Motorq scale, we needed proper governance of the data for a lot of compliance reasons. And these tables are now registered using the Iceberg REST catalog, and this can either be Polaris or Unity catalog and what other catalogs we have, and then this source has the single source of truth for all our downstream query engines. So Snowflake, what happens is they directly connect to the same Iceberg tables. There is no duplication. There is no second copy of the data. It's just one trusted data. Like previously we had to have Azure, we had to move it to Snowflake and whatnot, extra copies were there. But it just has one copy of the data, and all our Snowflake internal and external consumers directly consume and query from that. But an important thing about Iceberg tables, we all must be aware it needs maintenance. Because without maintenance, these tables, the query performance starts degrading. And that is where we start having our own compaction jobs that runs periodic maintenance to ensure that the performance of these tables are reliable, predictable, and controlled. So now let me pause here and talk about like one of the biggest problems like every one of us have faced, right? Schema changes. Previously, how it looked like is every time we made a schema update, we had to redeploy like hundreds of our ETL jobs and pods, because we had to ensure that the testing was proper and the quality was always like a little bit, we had to make sure that it's proper, and there's always the risk that something can go wrong in production in downstream. But with the schema registry, we started to leverage this to ensure that this pain point is addressed properly. What happens now? Now what happens is producers encode the message before publishing to Pulsar topics, and these schemas are validated and enforced at a per topic level. So each tenant also I mentioned is mapped to a particular namespace, ensuring isolation. So how does this help us? It ensures that there is consistency at the source, because there is, if any breakage or any schema failures are there in the top layer, it's not propagated down to the downstream layers. We are stopping it there itself. And it also ensures there is a faster development cycle for all our Motorq engineers. I mean, our developers no need to focus on deploying hundreds of pods, and every time there's some minor schema tweaks. It saved us a lot of time. And there's also reliability at scale, because now only the trusted, validated data from the start is propagated downstream, which our data science team and all other ML workflows can act on. So the schema management turned our daily fire drill into a proper enabler of both speed and efficiency. But now in the next step, let's say that once the messages are validated and it lands in the Pulsar topics, what is next? I mean, they just don't sit there, right? That's where StreamNative's compaction jobs comes in. They interpret those particular data by using the same schema which he registered in the schema registry. So there's like a consistent view between the streams and the data residing in the tables. But still there's like not every record is like perfect, right? There can always be some schema mismatches, some bad records, and even some failures that can happen in the StreamNative ecosystem, right? So what happens is instead of breaking this, these records are diverted to a dead letter topic and table. So why does this matter for us? It ensures that only the valid data flows into the Iceberg tables, which is instantly queryable for our downstream consumers and customers, and the errors are not just vanishing. They are captured in the DLT table, so ensuring that it's for auditing and debugging purposes. So what we do is, once these records are fixed or acted upon, we can just ensure that the good data like seamlessly is flowing into the table, and the bad data is but quarantined and it's never lost for us. We can do the fixes and we can then propagate it into our system to ensure that there is no data loss. But if you think about it, when we think of scaling data, right, it's just also not only about speed and cost. There is also another layer for governance, because governance is critical. We need to know who owns what data, how access is controlled, and how we make sure that every downstream consumer is using the same trusted version of the data. So that's where this open catalog comes in. We think of this as like a governance layer for all our data downstream. So it stores all the table definitions in one place. So whether you're using Snowflake, Trino, or Spark, you're just looking at the same exact metadata, and depends on the engines on how they leverage that metadata to ensure proper query performance. So Open Catalog on a high level uses Azure service principles, because we are in Azure cloud, to generate the SaaS tokens. So what this means is that access is controlled, it is scoped, identity based, and there is like no managed keys or anything floating around which can cause a big security mess later on. And both StreamNative and Snowflake use this to read and write data. And most critical of that is all of this happens over a virtual network and private network, a private link configuration, which ensures that no traffic flows over the public network. And this strengthens both our compliance and security as well. So from a governance standpoint, what this enables us is it ensures that there is proper isolation between our customers and tenant data at the catalog level, which we can configure. It maintains a full audit trail of all the changes and accesses that's happening, and it guarantees that every team is working with the same data. So it's not just like a metadata management, but it's the foundation for our governance which we are thinking, and secure data sharing. So the next thing we have to talk about is query performance, because for our company, this is very important. Our customers expect fast insights, and if any query starts slowing down, it directly impacts their ability to take actions, because it's either live location tracking or whatnot that Karthi has mentioned previously. So that's very important for us. But here's the problem, right? Even though StreamNative with continuous ingestion and it's configurable, it lands in every 3 minutes or at a 128 MB threshold is reached, there's also the small possibility that a quiet number of small files can still get created. And small files mean slower queries and increased computer costs, because now the query engine has to scan more files, get the data, aggregate it, and present it. But on top of that, there is also the additional problem about snapshots. So snapshot, we can think about it as like a version of the table. And if you let too many pile up, the metadata gets bloated, the planning time increases, and the performance still degrades. And there are still one point which many people just discard is about the orphan files. Orphan files are mostly created because of, I would say, failed compute, right? Sometimes when downstream fails, right? So, but these still, though they don't impact much query speed, I would still say they silently start wasting the cost stage and storage and bloat the cost. So this is where we need table maintenance. Maintenance ensures that the system is lean and the queries are fast, predictable, and cost efficient. Iceberg spec, lucky for us, has already defined four core, I would say 4 to 5 core maintenance operations that every table should run on, right? The first is rewriting data files. This merges the small files into the larger ones, and the spec also allows us to define strategies like Z ordering, bin packing, sorting by the frequently used queries, and we can optimize the layout based on each of us individual query patterns on how we anticipate the customers to query the data. The second thing is rewriting manifest. Similar to the top one, which I talked about data files, if you think about the Iceberg spec, there is the metadata, there is the manifest list in the next layer, there is next the manifest files which point to the underlying data files, and then the underlying data files come. So once we rewrite the data files, we also need to rewrite the manifest, and because this keeps the metadata about the data files, and they can also affect the query planning. The third thing is about expiring snapshots. I already touched about how the snapshots represent a version of the time which can be used to do time traveling. But we need to ensure that based on our use cases, we can expire these snapshots to ensure that the metadata is still lean and responsive. And the final thing is orphan files, orphan files are not tied to any snapshot, and we need to remove them to avoid wasting cloud storage and reducing the overall cost. And it is especially very important when we deal with the scale that our company used to deal with. So together, these 4 operations ensure that your table remains healthy, performant, and cost efficient. There is also another point about metadata overall which we can remove, and that's also another recommended operation from Iceberg spec as well. So I'll just close the loop on the maintenance job, right, on how we are running it cost effectively. So what we do is, instead of running these on heavy Spark jobs on regular compute, we just push them into cost optimized compute. These nodes are cheaper, and we are saving on infrastructure cost immediately. Now, there is always the case like how these nodes can fail at any time. Isn't this risky? But what we do is, we already know that maintenance operation that Iceberg specs recommends are atomic and idempotent. That means even if any job gets interrupted, we can safely retry it without corrupting the underlying data. So additionally, we have also enabled partial progress so that the work done before the preemption or anything is preserved and is concerned. So what this means, fewer files means faster queries. The reclaimed storage is keeping the cost lean. And by making sure that the table maintenance is running on cost-optimized compute, we are getting the best of both the worlds, both high performance and cost efficiency. So this is not just about running maintenance, but it's also ensuring that we run the maintenance in the most economical way possible.
Yep, thank you, Sai. So Sai had mentioned what are the benefits that Motorq would be reaping out of this. So let us look at some numbers, right? So numbers tells the true story, right? So here, we are comparing our current setup with what Ursa gives us. We looked at 3 parameters. First is latency, cost, and scalability. And latency being, it will be in the spotlight for us, because latency is what matters most to the customers, and serving it economically to them is what matters to Motorq. So let's look at the current setup. If you look at the current setup, the data latency is, it ranges from 1 hour to 1 day, which means it is dependent on customer use cases and the volume of data that flows into Motorq. So it is also a batch-based job. If you look at the infrastructure cost, we take this as the baseline for our experimentation. And the scalability is limited. Limited in sense, you will not be able to scale without putting a lot of money into it. You pay more to scale more. So let's say if we optimize the current setup, these are the numbers that it would look like. So we can bring down the latency from 1 hour to 20 minutes. We can optimize the batch size. We can tune the frequency at which the crons are running. But it will increase our infrastructure cost. It will go up to 2 to 3x higher. And the scalability, as I mentioned earlier, will be linear. The more you pay, the more you scale. Then let's say if we go into the next level, next-gen architecture, here we have near real-time data being synced into the lakehouse. It will be like less than 5 minutes. So we can even go sub-second latencies, but that would not be economical for our customers and our use cases. So sub-minute latencies is what is the sweet spots for us. So what it did to our infrastructure cost, we brought it down by 2.5x the original or the baseline cost. And the scalability is elastic in nature. So it means we don't over-provision all these compute for the ETL jobs. Everything is provisioned accordingly. And what is the final impact for us? The data is 12x faster available to the customer. We were able to use our resources efficiently. And this eliminated a lot of infrastructure bottlenecks in our system, either both the DevOps cycle as well as the SRE cycle. Now, let's look into the monitoring and observability parts of the system that we built in Motorq. At Motorq, we ingest massive amount of vehicle telemetry data in real time. Our pipeline needs to push this data into Lakehouse for downstream analytics, customer dashboards, and ML-driven insights. For us, observability isn't optional. We need not just know the data is flowing, but we need to know how fast and how reliable it is. So we have a few examples over here. The first image tracks the P99, P50, and max of how much time it takes for Ursa to load the data into Lakehouse. So this is like available out of the box. In previous architecture, we used to build this metric ourselves. Like we used to have a lot of custom metrics built, and we used to scramble around a lot of data to get the same metrics from our previous architecture. So this is available out of the box. This gives us an overview on like what is important to us and like what is important to our customers. And second, like we also have the compaction jobs running in Ursa. So this says that with the experimental load that we were loading, it was able to keep up with the load and it was not lagging behind. So this is also one of the important indicators for us, and it's like available right out of the box. And it's not only the metrics that is available right out of the box, but we also have custom metrics and custom dashboards built on top of the Prometheus endpoint Ursa provides with us. So for us, Ursa collapsed Kafka, connectors, and ETLs into one single step, and these charts show the operational simplicity and transparency that comes with it. So at Motorq, right, like it's always like other systems. Like we have seen how Ursa helps us, like, unifying streaming and Lakehouse ingestion today. But like any other production systems at Motorq, there's always the next step, making it simpler, cheaper, and more adaptive. So today we run the Iceberg table maintenance jobs ourselves. So it does compaction, clustering, and cleanups. That means we are spending engineering cycles on infrastructure needs instead of product value. The next step is to migrate these maintenance jobs into a managed service. These managed services can optimize based on the query patterns and eliminate our custom jobs. This will also reduce operational overhead and frees our engineers' time to focus on customer-facing features. Next, as we saw, schema evolution is critical for us. Vehicle telemetry evolves quickly. New fields, sensors, and event types are added all the time. Our goal is to ensure that these schema evolutions are seamless. When you define a change once, we want to have it automatically deployed across all customers and Lakehouse tables. This avoids breaking the pipeline during upgrades, ensures Motorq customers always sees consistent and up-to-date data. So in short, our future work is about removing maintenance toil and making schema changes effortless. That means faster iteration for us and fresher insights for our customers. So yeah, before I wrap up, I want to share a quick note on Motorq and some opportunities we have open. At Motorq, our mission is to unlock insights from our connected vehicles, helping fleets, OEMs, and partners build smarter, safer, and more sustainable mobility solutions. We've already seen how we think about data platforms like Ursa and the Lakehouse. We always have an eye with scalability and cost efficiency and speed to insight. To take this vision forward, we are growing our team. We are hiring for an AI product manager who will be helping us in building intelligence on top of our data platform, and a US market product manager who will drive adoption and customer success in our core markets. If you or someone else is passionate about connected vehicles, AI, and building at scale, please come talk to us after the session or reach out to us directly. We love to connect with you, and thank you again for your time and attention today. I would look forward to continuing this connections with you guys. Thank you. Now we open up with the questions.
I would also like to, a special thanks to StreamNative and Hang, who's present here, for helping us with our partnership. Looking forward to working more soon.
Yeah.
You mentioned future work moving the table maintenance into a managed service, and you're doing table maintenance yourself right now. But you're using Open Catalog. Open Catalog supports some maintenance operations on Iceberg tables that were written externally, like expiring the snapshots, removing the metadata, doing compaction, and so forth. Is there any reason why you're not using those features of Open Catalog?
So I can take it up. So these features have been released in a private preview. We are actually experimenting with them right now with Open Catalog.
So you mentioned that there's a latency between the Ursa to the Iceberg file is about 5 minutes. That's the sweet spot that you guys are targeting. What is the motivation behind that? Is it because of too many little files, or is it more technical reasons? Is there any other technical consideration that you run into?
Yeah, I would say it's because of the small files. We don't want to create too many small files as well, because when we did our experiments, the query performance was getting affected when we reduced latency. So we went ahead with the 3-minute threshold to ensure that we take a balance, because there's always the fact that until we run our next maintenance operation, whatever is returning there, those files will still have not a optimal query performance, right? So we took this sweet spot and the balance between the two.
Gotcha. So it's like a 5-minute cadence, and what is a file size you were expecting after 5 minutes?
So yeah, it would pretty much be, I would say, we have varying data thresholds, but it would pretty much be between 20 MB to 100 MB, which will be lands on it. Well, thank you, everyone. And yeah, if anything else, please do talk with us. And thank you.
Thanks,
Yeah,
everyone.
thank you.
Thank you.